if you observe that the energy, the way in which g of t minus u e raised to the power j zeta t. Now, the the way in which it behaves, I'm trying to explain. You can derive the statements which I am trying to say, but for now, just try to get an intuitive feel. In STFT, if you go to any point, like for a particular u comma zeta, the sigma t and the sigma omega at any point do not change. So in that sense, this sigma t and sigma omega always remains the same, and therefore we call this as translation invariant. So the time frequency atom in STFT is translation invariant. In that sense, if you go to any particular u comma zeta and try to calculate the sigma t and sigma omega, they will remain the same. But this will not be the case in wavelets. Now let me explain what will happen in wavelets. In wavelets, what is the formula? F of t psi of t minus u by zeta, or t minus u by s. Okay, this is what is the formula for wavelet. CWT, continuous wavelet transfer. So now let me take an example. Always one important property in continuous wavelet transform is that, or let me say, it will never be 0 omega, that omega, g of omega, or psi of omega, okay, psi cap of omega. That wavelet transform will be something like this, which will have some maximum. It will be some sort of a band pass filter. Why will it be band pass filter? We will understand it, but for now just understand that it will be some sort of a band pass filter. So now when there is a higher, so let me say that it allows this band of frequency to pass, centered around, let me say, omega naught. Okay, understood or not? So let me say that if the scaling is equal to 1, this is frequency, okay. So when the scaling is equal to 1, it centers it around some, let me say here only, some omega naught, when scaling is equal to 1. And let me say the shift is also, this shift is equal anything, okay. So this is my sigma t and this is my sigma omega, okay. But as soon as, if so, you are getting it that it is centered in frequency around omega naught. But now if I increase the scaling equal to 2, so scaling happens at so there is a dilation. So what is happening? That there is a dilation in time by 2 and compression in frequency by 2. So whenever there is the scaling becomes 2, so it means that frequency spectrum will get compressed. So now this will become omega by 2. So the centering will become equal to, let me use this red pen. So now the centering, this was for scaling is equal to 1. For scaling is equal to 2, the centering will be around omega by 2, and in the time the centering, in the time it will become, the window will become stretched by some factor. So in time it will be stretched or dilated. So now the figure becomes something like this. This becomes equal to S times sigma t. This becomes equal to S times sigma t. Let me show you. Because this is increasing because of the dilation in time. For example, you know na, that if this is the time frequency, if I reduce it, it becomes increased in frequency. If I reduce it, it becomes increased. So there is this scaling factor is increased in, this scaling factor leads to, what is the Fourier transform first of all? Psi of S times, this will become psi of S times omega into S times psi of S omega, this Fourier transform this will be. So in that sense, just for now, understand this main point, that if you observe, then there will be dilation and this will be this contraction. So sigma omega will become sigma omega by 2. And suppose you take this scaling factor is equal to 2. Now if I take the scaling factor equal to 2, just tell me, it means that in time domain, so in time domain there will be a scaling factor of, what we can say, 2 raised to the power minus 1. So this becomes psi of 2 times t minus tu, because scaling factor is 2 raised to the power minus 1. So the time compression leads to frequency expansion. So when scaling factor is equal to 0.5, it becomes, so the frequency becomes expanded. So this was the original and now it will become something like this. So if this was omega naught, this will become 2 omega naught, for scaling is equal to 2 raised to the power minus 1. So it will become, there will be an expansion. This will become 2 times sigma of omega. This will become 2 times sigma of omega, and this will become sigma of t by 2. Or for any general scaling and scaling, it becomes S times sigma t, and this becomes sigma of omega by S. So this is how you are able to see that how there is this time frequency is behaving by the way the changing by the different scaling factors. So it is not even. So we tell such transform, which we are calling wavelet, as translation variant. So in that sense, the nearby frequency, this nearby frequency will be grasped with with wide band in time, and the far away frequency will be grasped by a small narrow band in time. Okay, so in that sense we have got a very crude idea of how the time frequency atom behaves, and this is very important. So how will it be, how will the overall figure be? Just let me draw it. Okay, it will be something like this. Okay, something like this. Okay, it becomes smaller and smaller. So some sort of this kind of graph is how. So it is this kind here and it is that kind here. So the sigma t and sigma omega constantly keeps changing in a very different fashion. Okay. So by this we